going to look at the simulation to determine the things that are important when we're thinking about projectile motion and what's not important. A few things I want to point out. First of all, you will notice that we are at 0 degrees on our angle. We're going to shoot this straight out, and we are shooting a pumpkin. It's only 5 kilograms. We have gravity at what it's supposed to be, obviously. And we have no air resistance. And we've taken air resistance out of the equation because, remember, we're ignoring air resistance. We know air resistance slows things down. That's logical. But we're removing it because we're not ready to deal with it yet. It's a very sophisticated kind of calculation. It requires you to know things like humidity and altitude and all sorts of stuff. And once you get to university level physics, they'll add that in. But for the moment, we're going to pretend it doesn't exist. So we're in an air resistance free zone. So I'm going to start by shooting off my pumpkin to see what happens. There it goes. And you can see the path of that pumpkin. First thing I want to do is check to see how much mass makes a difference. So this was a 5 kilogram pumpkin. And we're going to change it to something a little more interesting. Let's try a human. A human's always fun. So he's 70 kilograms, much more massive. So in your head, decide shorter, further, or the same distance, because those are our only 3 options. Here we go. We'll fire it off. That's a very special human, able to stand up at the last minute. But you'll notice it landed in the same place as our squashed pumpkin. And that's because mass doesn't matter. Remember, everything's going to accelerate at the same acceleration due to gravity, no matter its mass. What makes a difference with this is air resistance. Air resistance creates a different terminal velocity. And that's why people think things of different masses drop at different accelerations. But that's not true. They all accelerate at the same rate. Okay, so let's try a couple of other things. The other things we can look at are things like speed. Speed is a pretty obvious one. We'll clear our board here. You'll notice right now we're at 18 meters per second. Let's pick something else to shoot just for fun. How about a nice piano? And we're going to shoot this nice piano out at 18 meters per second. And it should land basically where our girl and our pumpkin did. Now I'm going to make some changes. I'm going to reduce my initial speed to 9. So half the initial speed, went from 18 to 9 meters per second. Think in your head, shorter, further, same distance. This one's pretty obvious. It doesn't go as far, right? Because it doesn't have as much speed. If I make that speed higher, we'll up it to 29, the maximum, and you'll notice it flies right off the screen. And that's because speed makes a really big difference. The initial velocity, what it's launched at, is very important. So we'll be looking at that in our calculations eventually when we get there. The other thing that's important is angle. Because if I go back to my original, we'll go a little less. We'll go about 12. That should be good. If I look at this, then there's my piano. Oh, I hit the target. I got a star. If I change the angle now, so I make it shoot up into the sky, we'll say 20 degrees. This is going to make a big difference because before, all it was doing was going straight out and falling. You'll notice I only have half a parabola. When I shoot it this way, I should see more of a parabola. It goes up before it goes down. That's changed how far it went. If I continue to raise it, let's go with 35. That's pretty well, 36, close enough. Up and down, right? Slightly different spot. 44. Up and down. You'll notice the other thing that matters is your angle.